Sorry. I thought your voice. Okay. Sorry. Yeah, so my team has been developing methodologies for different applications about sequential decision making. For example, like in cancer and chronic disease, HIV and COVID-19. And today I will focus on the HIV. Okay. So what is HIV? So we know HIV stands for human immunodeficiency virus. So it's a virus that attacks human cells. And here, basically, I copy paste from Wiki, and it shows the steps of the HIV virus attacks human body. So it has several steps. So for example, like first one, they need to bind the host cell, and the second one, they enter the cell and then replicate themselves. So there are a lot of ART drugs now, and different ART drugs, they target different mechanisms. So for example, there's a class of ART drugs called NRTs, it's nucleoside reverse transcriptase inhibitors. They specifically inhibit this step. Okay, so but there are multiple classes. They target different steps. Okay, so here is a list of common ART drugs people usually consider. And we can see there are 5 classes. And I will not repeat their names because it's just like FDA-approved drugs that target different mechanisms of the HIV infection. And interestingly, because HIV virus is also RNA virus, so at the beginning of the COVID pandemics, and people actually tried a few HIV drugs on COVID-19. And actually, they also tried that in Ebola. So like RTV and LPV. So these 2 drugs were first used for treating the COVID patients.
Just to clarify.
Yeah.
Do you directly use the HIV drug to treat the COVID?
They directly try that because it's RNA. It's all RNA. Sorry, it's all RNA virus. So and also these drugs also was used to treat Ebola. So they first want to see if this actually works for COVID. Yeah.
A lot of the HIV drugs are treating viral infection, or hepatitis, some of them, not that kind of drug. It's universal.
Yeah. 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 Thank you for mentioning that. Yeah, Jay is an expert in HIV. Okay, so for like when we prescribe the ART for HIV, and people have already found out, one single drug is not working well. And then people find out like a cocktail approach is a combination of ART works best. So essentially a combination ART means like we want to choose the different ART drugs from different drug classes so that the combination of them can target multiple steps of the infection process. So for example, we can prescribe like a combination with 3 drugs and 2 of them are from ARTI class and another one from INSTI. And another example could be 2 ARTI drugs and 1 NRTI drug and 1 PI drug. So essentially, it's a cocktail approach. It's kind of like a standard practice for treating HIV patients right now. Okay, so in clinical, the HIV people usually they are recommended to visit the clinics every half year. So they, on average, they have semi-annual visits, and at each visit, their record will be, the physicians will check their records. For example, like social demographics. And the lab tests like HIV viral loads and also the CD4 counts, and also the behavior characteristics, for example, like drinking, smoking, substance use, and also some clinical factors, for example, like BMI and also kidney function, liver function. And the clinicians will check these measurements, and then based on these measurements, they assign the ART regimens. So they want to say, okay, what's the optimal regimen for them based on their records. And this process basically repeats in every visit, like every half year. Okay, so then why do we want precision medicine in HIV? So currently there's already guidelines. So the DHHS, they have already issued a guideline for treating HIV patients. And they have very comprehensive guideline for treatment-naive patients. So that means if they were just newly diagnosed with HIV and they never used the HIV drugs before, and the clinicians usually follow the guidelines, so how to initiate their treatment regimen. However, for pre-treated patients, so for example, like the the data we analyzed in MaxY, so I will introduce more like, they have been on HIV drugs for decades, like 20 years, 30 years. And what's the optimal regimen for them? It's still unknown. Because there are a lot of things we need to consider. Because first, when people have HIV for a long time, and there are some like, they call like some memorable effects is that, there could be some long-term side effects from the HIV virus for like, mental health and also cognitive impairments. And also these drugs, these patients are using these drugs for like 20 years. We know these drugs also will have side effects, right? So they will have side effects on, like here, kidney function, heart function, and anxiety, mental health, these kind of issues. So there are a lot of information to consider when we prescribe the regimen for patients. So our goal is to determine the personalized ART regimen to optimize the patient's long-term health. Okay, that's our overall goal. And also developing these kind of methods has society impact. So we're currently building software. So imagine if we can have this software and the clinicians can use that to treat patients, then it can help, improve patients' outcome, right? So for example, we know like, quoted by the academic executive director. So he said our patient population is growing, but the number of medical professionals specializing in HIV care is not keeping pace. So it's actually now happening in US. So if you go to a lot of like rural regions of United States, and HIV people actually treated by their primary physician, and their primary physician may not specialize in HIV. And not to mention there are a lot of developing countries, like we now have collaboration with, people in studies in Uganda and other countries in South Africa, and they don't even have these well-trained physicians. They have these community physicians to treat patients. So we are trying to build this kind of software so we can help the clinicians or like the community physicians to treat patients. Okay, so here is the background. So now let me talk about the data we analyzed to help achieve this goal. So we use the data from large-scale HIV studies, MaxY's combined cohort study. So the MAX was a prospective cohort study since 1984, and it mainly recruited men with HIV. And the WISE is another study focusing on women with HIV or at risk with HIV. So it was started in 1990s. And they recently combined two cohorts. It's called MWCCS, it's MaxWise combined cohort study. So we have like several thousands of participants here, and they have been followed up for up to 30 years. And on average, they have semi-annual visits. And at each visit, we recorded their ART regimens. So for example, here, the x-axis is the calendar dates of their visits, and y-axis is the number of drugs they used. So we can see the pattern, at the beginning, they have monotherapy, only one ART drug. And now, people have cocktail type of treatment. They have multiple drugs from different drug classes. So here's the letters is the drug name, and the different colors represent different drug classes.
So Max cohort study, the men, they are gay men cohort, right?
Mainly, yeah. I think at the beginning it's mainly the
So
homosexual.
women, are they lesbian?
No, the women is all
General.
Yeah, general. Yeah, actually, that means not to high risk for HIV. So yeah, it's more like women, even already diagnosed with HIV or at risk of HIV. For example, they have some partner or like. Yeah.
Both cohorts, they are like, what's the inclusion criteria? How they get selected into enrolled in this cohort? Are they already diagnosed or?
No, it's more like diagnosed all at risk. So
they
for
are,
example, if
they are
you-
they're recruited because they're high risk, but not necessarily already diagnosed.
Yeah,
Not
actually, there's a
necessarily.
lot of research.
Yeah, that's why I have.
For Max men, the many gay men are, they were sort of two types of cohort. One is the incident cohort, healthy gay men, enter the study, but there's another group, it's a prevalent cohort.
Oh, yeah.
They were already HIV infected.
Okay.
I think they're actually doing that. I did a lot of research in that class. So they're basically community cohort settings. So when they recruited people, the only criteria is their risk profile. For example, if men is men who have sex with men, and then they test their HIV status. So it's not like creating two separate cohorts, they're just recruiting the whole group and see how many people actually have HIV. And there are actually because the cohort started in 1984, they actually have a lot of serial conversion cases because this is still a high risk.
Yeah.
Similar to
Yeah, and also thank you for and also there are several waves of recruitment. So at the beginning, and then I think the recent is like 2000, they have like 4 or 5 waves of recruitment. Yeah. Okay, so here is the drug information, and also at each visit we have their health-related environments recorded. For example, like here depression level, like it's measured by CESD, it's a question now, and also like very low EGFR representing kidney function, and also BMI. So of course there are missing data, but just here is illustration. Okay, so it's basically we have several thousands of participants, and we have longitudinal data, and at each visit we have their drug information and also a lot of other health-related environments. Okay, so what's the challenge? So now we have the data, and to answer this precision medicine goal, and what's the challenge? The first challenge is we need to first estimate the effect of ART regimens from a high-dimensional and unbalanced space. So when I say high-dimensional, it means with more than 30 ART drugs on the market, there are a large number of possible drug combinations. So for example, in MaxWise, we found there were like over thousands of possible drug combinations that were prescribed for participants. And when I say the unbalanced, it means some drug combinations are frequently used, some are not. So for example, for this drug regimen, like 2 NRTI drugs and 1 PI, it was recorded about 1,000 times in the data. However, another similar regimen, 2 same NRTI drug, but another PI drug, it was only recorded 12 times. So we can see these very similar drug regimens, but they are very balanced. So we need to estimate the ART effect from this high-dimensional and unbalanced space. And the second challenge is we need a way to generate a realistic ART regimen from a large discrete space. So you can see here we have these drug combinations, right? Essentially, it's a combinatory problem. Like you need to choose drugs from different drug classes. And the way how we generate is like, the essential problem is how to represent an ART regimen. I would say a straightforward way is we can just use a binary vector. So let's say we have n individual drugs, and we can have this n-dimensional binary vector with each dimension representing whether this regimen has this specific drug. However, it doesn't work. The reason is that if we have this binary vector, then each one could be 1 or 0, then you have 2 to the n possibilities, right? However, with over 30 ART drugs, most of these 2 to the n possible combinations will never be prescribed in clinical practice. So this is not a good way to represent. Okay, so that's one challenge we will need to address. And the last one is we're essentially optimizing treatments from observational data. It's not clinical trial data, so it's observational data. And sometimes this problem also called distribution challenges. Okay, so here is our roadmap of precision medicine HIV. So first we need to understand the ART effect, and then we need to find ways to optimize ART. And lastly, we also need to incorporate domain knowledge because there are treatment guidelines, and also there are drug interactions, and a lot of domain knowledge we need to incorporate to our methods. And then we can get our holy grail. It's user-friendly too. That's software. Okay, so I will briefly touch each part of them. So I will not delve into super detailed technical details, but if you're interested in that, we can talk after. Okay, so the first part is how can we understand the ART effect? So here are some notations. So let me use some depression item as an outcome for illustration, but we studied all the outcomes. So here YIJQ denotes the score of depression Q for individual I at visit J. So because we have participants, different visits, and there are different outcomes, so we have this YIJQ. And also we use ZIJ to denote the ART regimen used by individual I at visit J. So for example, ZIG could be D40 plus LM plus NFP, where these are regimen. So we can see here is not regular that Euclidean, like binary vector type of thing. So the Z here is kind of like the key parts in our model we need to address because it's a drug combination. And XIG is just other covariates we need to consider, for example, like, time invariant covariates like race, and also time variant covariates like BMI, CD4 counts. Okay, so here is the overall model. We essentially decompose the modeling of YIJ as a vector to multiple components. The first components we call the non-ART effect. So non-ART effect here, we just adopt regular, like linear mixed effect model. It's very standard. So we incorporate all the demographic behavior kind of clinical variables into this non-ART effect part. So just linear mixed effect model, you can imagine like that. And the key part is how can we model the ART combination effects? That's a drug effect. So we know this ZIG is high dimensional, right? So we have a lot of possible drug combinations. So we want a way to reduce dimension so that we can model this drug combination effect effectively. So we have two desired properties. The first one is we want some sharing of information among similar regimens. So for example, if these two regimens, they both have two NRTI drugs and one PI drug, they should share some information, right? Because drugs in the same drug class, they share the same mechanism. So we want the sharing information among the regimens. And the second one is we want it to reduce the high dimensionality. So we take a kernel type approach.
I'm not sure if you mentioned, so I is the subset index.
Yeah.
And J is the
Visit.
visit index. So what's Y?
Y is all like possible outcome like depression, EGFR, and
So
also.
you are assuming that the drug effect is immediate.
Oh, okay. So very good question. It's a simplified model, I would say, because for the
Okay.
presentation purpose, we actually have the like incidence effect and also historical effect. But
Okay.
because the idea is similar, so I only include this part
Gotcha,
for simplicity, just for presentation. Yeah.
Also, the other one is that you said visit, but the patient may have not same visit schedule.
Oh yeah, that's true. So that's why you see here it's more like linear mixed effect model type of thing, because in the linear mixed effect model, each patient doesn't have to have the same schedule and the same number of visits. Yeah. Okay, so we adopted this kind of like kernel type approach. So the key idea is we introduce a bunch of ZD. Here are the representative regimens. So we call them representative ART regimens. And then we introduce this similarity function. So it's kind of like the kernel or the like spline, like the knots, right? So it's like you have these knots and then you calculate similarity, and then we reduce the dimension of all the drug combination spaces to only D dimension. So think about this representative drug regimen maybe like 50, for example, and you can reduce this 1,000 dimensional space to this 50 dimensional space. Okay.
So
And-
one more question.
Yeah.
So your model, you don't care so much about the so-called starting point, right? So how
Yeah.
long the patient, HIV patient has been infected?
That's very good question. So yeah, we don't have that part, but for X, you can think we actually included the duration of each individual, like how long they have been using a certain drug.
Okay,
Because for these cohorts, not all the patients are newly diagnosed, right? We don't have their historical, like, when they were
Okay.
diagnosed. We
okay,
don't have that information. So, yeah, but we include some like, historical, like, how long they have been using like IRT drug.
It
Yeah.
seems that you use the same H function, so I can see that here, same H function for all the ZIG, IJ. So ZIJ are different drug combinations.
Yeah,
So that
they,
means they have the same function, H to the Y.
oh, because the H, you can see here, it's parameterized by gamma ID. So it's indexed by I and also the regimen. So so it's like the knots idea, so like spline thing. So the H, we just read H, but the parameter actually is gamma ID. So it's like subject specific and also the regimen specific.
So H should be a function of I and J.
Yeah, it's I and J and D is the regimen. Yeah.
And how did you deal with computation bias? I mean, a lot of people switch and drug because of, say, for example, the EGFR kidney function get that. So this, but how do you differentiate that from this dispute outcome?
That's very good question. Yeah, we didn't distinguish from this type of model because kind of like you need to guess, for example, what's the reason for their switch. And also, that could be also like, that could be resistant mutations. So we don't have this kind of data. So I think that will be the part I will include at the end. So it's like we are kind of, utilizing the tools like large language models to help on that perspective. Yeah, but here it's just like we just only based on the available data. We don't do any educational guess, for example, what's the reason for the previous switch thing. Yeah.
How do you determine the similarity between a less used ART regimen with the representative one?
Very good question. Next slide. Yeah.
And in this model, how do you account for distribution shift problem?
Oh, that's the next part.
Okay.
Yeah. Thank you for your questions. Yeah, so yeah, last two parts also is like dynamics effect model, very standard. Okay, so how can we define the similarity? Okay, so that's a key. I think that's my favorite part about this model. That's kind of like our key contribution. So think about how do we represent the similarity? A naive method, I would think, is like linear kernel. We first thought about the linear kernel. So linear kernel means we just compute the similarity between regimens based on the proportion of common drugs that two regimens share. So for example, for these three regimens, they all share default T and LAM. So if we use a linear kernel, we know their similarity will be 2/3, right? Because you have three drugs in each regimen and they share two same drugs. But what is not enough? The reason is that if you think about the first, like the two regimens on the left part, both of them, they have two NRTI drugs and one PI drug. Even their PI drug is different, but they share some similarity, right? Because we know they share similar mechanism. So we would expect the left two regimens should share higher similarity compared to them with the right one. And another extreme example is here. You see these two regimens. Both of them, they use two NRTI drug and one PI drug. However, they do not share any single drug. So that means if we use a linear kernel, the similarity would be 0. However, we can still borrow some information from these two regimens. And then we adopt a method called substitute kernel method. So substitute kernel was originally developed in natural language processing. So, and the substitute kernel was used to represent the sequence structures. So this for NLP. But I kind of made the connection. I think maybe we can use tree structure to represent regimen. So here is the way we represent. So the first level would be just ART, and the second level represents what drug classes this regimen has. And the third level means how many drugs in each drug class. And the last level is each individual drug. Okay, so the reason why we want to represent at this tree structure because that the substitute kernel actually can calculate the similarity between regimens across all levels of tree representation. So for example, if you see the regimen A and B, the blue color parts, they are the same. So they can actually calculate the similarity among these two. And between the regimen A and C, you see the yellow color. So even their bottom level, the exact individual drugs are different. But the yellow part, the both regimen contains two NRTI drugs. So we can borrow some information. So for example, like the panel D is a similarity score we calculated for regimen ABC. So we can see A and B has higher similarity compared to A and C. And also if you see the diagonal values, they are self-similarity. So we can see the self-similarity for regimen C is higher than A and B because C has 4 drugs and A and B only has 3 drugs. So we know it's harder for the 4 drugs to be exactly the same compared to the 3 drugs.
So when you look at this similarity and difference, it seems like you assume that two different subgroups, they differ only by the drug they used, but there are all other patient characteristics.
Oh, here's by patient visit level, it's each individual one. So if you see the similarity, you see it's ZIJ and ZD. So basically you get the regimen for each participant, each visit, and you calculate the similarity. So it's not by some population level, it's just, it's individual level. So essentially we have, for each individual, you have this drugs like similarity.
So you mean this table is derived?
It's
from
regimen
a
level.
Single patient.
No, it's for the regimen level, not the individual level. So you can think about for here, like if data we have 1,000 possible drug combinations, and we will calculate 1,000 by 1,000 similarity matrix. And for each patient, you just get one of their values to calculate their similarity with this representative ART regimen.
Right. So this is what I'm saying. When you created this matrix, so you are using multiple patients.
Oh, just
You are not using one patient data.
but the regimen level, they are so those patients, if they're using the same regimen,
Right,
they're
if they all use the same, that's what I'm saying. If everybody is using the same regimen, they are still different, those patients.
oh yeah,
Even for those patients who are using another regimen,
right.
the difference between the regimen or their similarity or not similarity, not just due to the drug. they
Yeah.
use.
So yeah, that's a good question. So you see here, so the left side, the ART regimen similarity part, we actually have, so that's why I said in a simplified model, we have another term to have like interaction between the X and also the drug effect. Yeah. And again, this similarity is on regimen level, not the individual level, just regimen level.
That's why,
Yeah.
when you look at the regimen level, you are considered patients are homogeneous.
Right, yeah, of course.
Only due to the regimen.
Oh, but the whole model, we consider there are other, like X, like all other health measurements and CD4 count viral load. We have all those parts we
But
consider.
on this table,
Oh yeah, this table we don't, because it's just regimen. It's just like the ART regimen similarity. Yeah, because we want to incorporate the clinical knowledge about the drugs themselves, not about the patient thing. It's just like the drug, the similarity between this drug and that drug. That's all.
yeah, that's what I'm saying. The
Yeah.
patients who are same regimen, different patients, they
Yeah.
respond different.
Right, yeah. Okay, okay, yeah, so with this substrate kernel, oh, it's here, okay. I just skipped the formula, it's just a way how to calculate the drug similarity, yeah. And here is the overview of model. So we model the outcome Y as we decompose them to non-ART effect, ART effect, and some error. And also because the population is heterogeneous, so we use some pri. It's Bayesian non-parametric pri. It's called Chinese restaurant process pri. And we assume different subgroups have different effects. So yeah, but this is not the key in this paper. Okay, here's the reference. And let me show you the results. So our method can basically do the individualized prediction of the ART effects. So here is an example. So this person has 6 visits in the data. So we have their age, BMI, CD4, viral load, hypertension, substance use, and the smoking status. And also here is their the ART regimen they have been using for the last 6 visits. And applying our model, we can do the prediction. So for example, here, if we want to decide what's the best regimen for the next visit, and we consider 2 possible regimens. So the first one is LAM plus AZT plus LPV, and another one is EFV, TDF, FTC. So basically, our model can give you see the prediction. So the bottom panel is a prediction, and also we have the prep interval. And based on these results, we can compare, what's the predicted outcomes if you were under these regimens, and then the clinician can make the choice. Okay, and here we have, so actually Wei is the one who did all the analysis and also made this R-Shiny, and it's still online. If you're interested, you can try it. So it's like, you input the patient's information and then we will give you the prediction. Okay. That's the first part. So like, how do we understand the ART?
So for the information you enter, you must give like information of 6 visits.
Yeah, the historical.
Historical, but in fact, if a patient has a 5 visit, no historical record 5 visits or 3 visits.
It's okay. You can.
It's okay. Okay, adjust it.
Yeah, just adjusting that. Yeah. So you can, because this information you need to.
So it's kind of like a dynamic type prediction.
Right. Yeah. Yeah. So that's the first part. We like how to understand the ART effects. And for the second part, after we understand the ART effects, we need to find ways to optimize them. Okay, and like I said, the optimizing ART essentially is a sequential decision-making problem. And for optimizing sequential decision, it's offline reinforcement learning problem. So we know the offline reinforcement learning has achieved a lot of successes in a lot of domains like self-driving cars. And for these reinforcement learning methods, there are really two major types of method developed. The first one is model-based method, and the second one is model-free method. So my group has been working on these two types of methods. So let me show you the model-based method first. So the model-based method, we develop a two-step approach. So the first step, we propose a Bayesian dynamics model to learn the underlying dynamics. And then the second step is apply a offline reinforcement learning approach to optimize the ART. So it's kind of like the difference between model-based and model-free. Like a model-based method is like you first learn a model for the underlying dynamics and then you optimize the actions. And the model-free is you directly model the action without the modeling the dynamics. So the first project we tried is kind of like because we are statisticians, so we want to try statistical method first. So we say maybe let's do the model first and see what it performs. Okay. So here the reference. So we formulated this problem as kind of optimization problem. So again, some notations. So we have baseline covariates xi0, and we have ti to represent the visit times. And also we have this yi denotes the m time varying health state variables like BMI, EGFR. This y is yi1 to yiji, and the gi is the number of visits each person has, and it's a multivariate dimensional. And again, zi is a treatment. Okay, and we have d to denote all our data. And also we introduce this y bar and the z bar. We follow the dynamic tree regime tradition. So we use y bar and z bar to denote the history of the health state variables and also treatments up to visit j. And we also assume, because we are learning a dynamic model, so we are assuming yij plus 1 follows of, condition on the whole past history of y and z, and it follows this dynamic model. Okay, so our goal is to optimize ART assignments to maximize the individual long-term health outcomes. Okay, so it's basically it's optimization problem. So let's assume for any individual I, we suppose she already had GI visits, and then let yi nu and zi nu denote her future longitudinal states and the ART regimens after the visit J. And we assume the policy is kind of like action, how physicians assign treatments. It follows ART policy function. It's pi, the Z as a treatment, conditional on the whole past history. And also we assume each person receives a reward function, Ri. It's a function of y nu and z nu. And then we can represent the expected reward. So it's kind of reinforcement learning. You need a reward function. So now we have this expected reward for each individual. Okay. And this part is expectation is taken over all the possible realizations of the future states because we don't observe them, right? So if we have model, we need to integrate out all the possibilities. So the expectation is taken over the y nu, z nu. And also this p phi condition on d. Remember the phi is a dynamics parameter. So that's kind of like the advantage of Bayesian methods here because from the dynamics model we learn the uncertainty and then we incorporate this uncertainty in the policy optimization. Okay, and the goal is we want to find a theta that's a parameter in the policy function that can maximize the expected reward. Okay, so that's basically is our optimization problem. Okay, so how can we do this optimization? So essentially we use a stochastic gradient descent. So stochastic descent means if we have ways to calculate the gradient of the expected reward, then we can do the optimization. So the essential problem is how can we calculate the gradient? Okay, and here is Ri theta, and luckily for us, here is a formula for the gradients. Okay, again, you can ignore all the details, but essentially to calculate this gradient, we have three parts to work on. The first part is the log policy part. Like we need a policy function. Okay, so that's one challenge we need to solve here. Another one is we need a dynamic model on the Y and the Z because we need to sample future states. And the last one is we need to define reward function. So essentially, the goal of this optimization, the solving this optimization problem basically boils down to these 3 steps. As long as we can sample future states, define reward function, and parameterize the policy function, we can do the optimization. That's all. Okay, so I will briefly introduce each part. The first part is how can we model a dynamics model. So here we actually borrow a lot of idea from the first project. Like we model the longitudinal data, and here we use a multivariate Gaussian process. Okay, so you can imagine the multivariate Gaussian process has a mean and the various covariance function part, and the mean part has those ART, the modeling the ART part from the first project. Yeah, and the reward. Okay, that's all. I'm not going into the detail, but basically it's a multivariate Gaussian process.
So you try to use what you learned basically from first project to summarize in a way in terms of MTP.
Yeah, so basically it's like we use a Gaussian process to model how these outcomes develop over time, and we include the treatment effects based on like the idea from the first work. Yeah. Yeah, but there are a lot of model details, so yeah.
Yeah, no,
Yeah.
sure.
And for the reward function here, we define the reward function in this project just based on very low kidney function depression in the next 2 years. But I need to say we can include a lot of other things. So yeah,
In your policy function, that's Z.
that's the action. Yeah,
So yeah, so that's discrete.
yeah.
So how you make
Good.
choose your policy?
Next part. So yeah, so for the sample, we have 3 parts, right? The first part we use the multivariate Gaussian process. Here, the second part is how do we define the reward function, and then I will go to the policy part. Yeah. So for the reward function, you can imagine basically it's a weighted sum, and we have depression, very low EGFR, but you can consider a lot more. So like in the work we just submitted is we actually consider a lot of physical health and mental health outcomes, but here just for illustration. Okay.
And you said it's in the next 2 years, so that's something that you.
So
Do you have that or?
right, so the reason why we want to only, in general, a lot of reinforcement learning, they focus on long-term rewards. But here we only want to focus on 2 years because, the HIV drugs are fast evolving. We have all these long injecting drugs, right?
Yes.
So we don't want to predict too long, but we also don't want too close to now. So that's why we choose 2 years.
Okay.
Yeah. I saw people they did like 5 years, but I still think 5 years is too long. So I only did 2 years.
No problem.
Yeah.
And can you explain me that this reward is that kind of subject specific reward? Or?
Yeah. It's you see it's why I think
Yeah.
it's subject specific.
Okay.
Yeah. And here, it's 4 visits, so 2 years. And we know the depression is smaller the better, right? And also for very low than EGFR, we know as long as they're in the normal range, then you don't need to optimize further. So we have this abnormal threshold. We only penalize them if they are outside of normal range. And also we have this personalized weight, the WI. It basically, like physician will need to determine that, for example, if you think mental health is a major issue, then you can assign higher weight on W1. And if very low is a consideration, you can assign W2 to a higher weight. Okay.
The measure of the weight is 1, right?
Yes. Yeah. And also for the distribution shift issue, so just ask, we actually address this problem by defining an uncertainty penalized reward. So essentially, we borrow the idea from MOPO. It's model based on uncertainty penalized policy optimization. It's by machine learning field. They develop a method. They basically modify the reward. They call that a pessimistic reward. So it's just essentially the meaning is that instead of using the original reward RI based on the health outcomes, we define a penalized reward, and it penalizes the uncertainty of the state action pair. So you can imagine if this drug combination has only used a few times, like 2 times, you don't really trust your inference, right? And this kind of uncertainty will be reflected by our Bayesian model because you have uncertainty quantification. So that's why we do this penalized, like if this state actions pair has high uncertainty, and we will penalize their reward. And they show this one can somehow mitigate the distribution shift issue. And in our case, because we have Bayesian model, and we just calculate the uncertainty this by the standard deviation of the Y conditional Z and D. Okay, so that's kind of another advantage of a Bayesian methodology because we have uncertainty quantification naturally. Okay, so we have these two parts. So sample future states define reward function, and the last one is how can we parameterize the policy function. So again, we use our tree representation. So that's why that's my favorite part about this whole thing, because I think this tree representation is really useful. So how can we model this policy function? So essentially, we build this decision tree. So in clinical practice, when the patient comes into the clinic, the physicians usually first decide whether you need to switch, right? Because if everything is normal, you don't need to switch the drug. So essentially, we first determine if we need to switch the regimen or not. So here we represent it as a binary thing. So if everything in the normal range, we just keep the original regimen. If not, we consider to switch. So if we consider to switch the regimen, then we need a way to assign the drug, right? So now we need a way to represent. And thanks to this tree representation, we kind of like simplify the problem of this combination problem to a tree selection. So essentially, we first decide which drug classes and how many drugs we want to use. So it basically is a multiple class logistic regression model. And also, if we determine that, and then what's the individual drug we need to use? It's essentially a non-central hypergeometric distribution. So I skip all the formulation here, but you can imagine our policy function is a combination of these three steps. So first determine whether to switch, and then if we need to switch, and then how can we draw the drugs from this? And this way also ensures we get a realistic drug combination, not just like binary vector type of thing. Okay, so now we have these three parts done, and then we can do the optimization. So let me give you one example. And here is one person from XYZ, and this person had 31 visits. And here is a drug history. And here we use the W as 1/3, 1/3, 1/3 because everything is relatively normal. And then here is the results. So the left part is just a stochastic gradient descent iteration. So we show it converges. And also the bottom part is the optimal regimen we predict for the next 4 visits. Okay. There is some clinical meaning behind that, but I will skip that. But we do the prediction, like for example, we predict that if this person used the recommended regimen, and the depression level will improve. So we can see here. So, and this is a person historical depression level, and there's missing data there. So, that's also one major reason why we use the multivariate Gaussian process, because it can handle the missing data very well. Okay, so we can see this person's depression can be improved by 23% if they use these optimized drug regimens. Okay. After we debug that method, so that's actually also we led the effort. So after we debug that method, and we figure out, so we build the software, we found it's too slow. Like the clinician basically need to wait 2 hours to see what's my optimal regimen. And then we start to think about, can we develop another faster method? Because our final goal is to develop a tool that can be actually used in clinical practice. So I have another PhD student who lead the effort. We call this as HIV AI care. So now it's under review at Nature Communication. So we developed a model-free method because we found out the model-free method actually, not just mentioning the performance, but at least it's super fast. So that's why we kind of came up a method. It's like offline. It's still a model-based. It's still a offline reinforcement learning method, but it's model-free. So here's kind of like the structure.
So the model you talk about, you just totally throw that out. So it's model free.
Yeah, it's model free. It basically like kind of you optimize the reward directly. So like you don't need to model the the dynamics model. But use a multivariate Gaussian process basically is very time consuming.
And why is faster? Why is faster?
Because it's like So model 3 essentially you can think about it calculate a Q function, it's like action value function. And basically you give the input as and it outputs the optimal action. So it's kind of like, for the model-based method, when we have the new patient, we need to retrain the model. However, for the model 3 method, when a new patient comes in, we just input the information, you can automatically output the optimal action from that Q function. So
you're not using like a generalized linear model, you use the Gaussian model, totally sort that
it's
out.
gone. Yeah, it's gone. So basically here we use we track the LSTM and also transformer. So it's more like a deep learning approach here. Yeah.
So totally different approach.
Totally different approach. Yeah, so the data is the same. So left side data is the same. And just the middle part, and we have this deep learning
So I
approach.
told you, she is really an expert for multiple areas.
So what's the optimal means here?
So optimal, you can
Optimal
think,
in what sense?
optimize the person's long-term health. So you can think about reward function similar than before.
Okay.
But now the reward function here, like for this work, we have been discussing clinicians for so many rounds. So in this work, we consider more things in the reward function. We basically consider like mental health and physical health. People usually use mental health, physical health to define a person's overall health, right? So for
it's
example, like
optimal in the sense that
like
maximize
depression.
the potential outcome. Not necessarily.
kind of you can think about, but basically you can think about the optimize depression, cognitive, kidney function, liver function, lipid function, bone health, and also cardiovascular. So we have.
Yeah, but they're kind of more or collectively considered just as a clinical outcome.
Yeah, clinical outcomes.
Of
Yeah,
interest.
it's kind of like the physicians, they care about them, so we include all those variables in our model.
So it's optimal in the sense to maximize the patient outcome gain or whatever. Something
Yes.
like that.
Kind of.
But for the outcome you talk about, you still deal with the one outcome at a time.
No,
Like
here,
a depression outcome, it's
Yeah,
depression.
that's another
You
question.
could have a.
Is that a multidimensional?
Right.
yeah,
outcome
so you
or
can
it's,
think about, it's a deep learning model, so you see the middle, I'm not sure why my mouse doesn't work, but if you see the middle part left panel, it's basically the Q learning, basically you input the state and the action. So the state now will include all the historical, health outcome, treatment, everything, and also the current. So you can think about all the outcomes,
all
and the
outcomes.
covariates, everything will be in the state.
But the current outcome is still one.
Multiple. It's still like, because now our outcome is like composite outcome. You have depression, cognitive impairment,
it's a component
Kidney.
or just a multivariate.
Yeah.
multivariate.
Multivariate.
Multivariate. Yeah,
Okay.
multivariate. So you can think about this HG, SG. So HG is all the history, and SG
Okay.
is current, like covariate,
Okay.
and also the outcomes and treatment regimen. Everything is here.
But multiple outcome, you're talking about this method,
Yeah, this
right?
method.
But
Yeah.
previous method, model-based method, you deal with one outcome at a time.
Oh, that's why it's also multivariate dimensional. So we
That why could be
It's-
also.
it's
okay.
multivariate also
Okay,
process. It's
But
not.
you were using depression as a some example.
Yeah,
Just an example,
Yeah.
but you could be
Okay.
multi-dimensional.
Yeah, so for the second project, we actually model several together. It's a multivariate development process. Yeah.
That's the critical is you put when you have a reward function, then it basically you put all these things,
Right,
it's a linear combination weighted.
Yeah, it's
Yeah,
kind of,
yeah,
yeah. But I think,
The way
yeah,
that-
Paul, you actually mentioned a very good point. I will talk about later. That's one extension we're working on right now. That's also a shortcoming of this method. Yeah, and here basically is the structure of the method, but I can skip the detail, but essentially we have we still use a substitute representation for the regimens. But now we use a PCA embedding to represent the regimen because we need to input like a vector for the deep learning models, right? So that's how we deal with the drug. And also the below part is we develop like history dependent, because traditional reinforcement learning method, they rely on the MDP assumption. It's a Markov decision process. But our process is not Markov, right? It needs to depend on the whole history. So we have this historical dependent deep learning approach. Okay, and here is the results. So essentially our methods, because we have this Q function, not only we learn the optimal action, but we actually have the ranking of all the actions. So I think that's also what physicians they want. They want to see a ranking of the regimen so that they can it can be flexible for them to make their own choice. Okay, so
Question. Yeah, I guess the weight has to be predetermined.
yeah, that's what I said. That's very good. I will mention that at the end. Yeah, so that's also one part of work we're working on right now. Yeah, so here are the results. So here is top 5 for 2 participants. And the upper panel, we can see the red color is a clinician policy. That means the clinician actually assigned this drug regimen to this person. And we dig in like why we prefer IL plus DRV plus RTV compared to the clinician policy. And we found out this person is depressed. So we can see the depression level is above the normal range. And we found if we plot the Q value versus depression score, we found out if for less depression people, the clinician policy actually is good. However, for highly depressed people, you see this cross. For highly depressed people, our recommended actually is good for people's mental health. Okay, so similar for the second participant. So essentially, our software is like this. You can input the patient's information, and it will give you the ranking of the regimens. Okay, so now we have the first 2 parts. And then we still get some regimen recommendations, not really, clinicians think is appropriate. So the next step is how can we incorporate domain knowledge? Okay, so we know guideline already have a lot of domain knowledge. For example, guideline says if this person has kidney disease, then it's better to avoid the drug TDF. And also if you have cardiovascular risk, it's better to avoid, ABC. So there are a lot of guidelines we should incorporate to our model. And also there are a lot of common information, for example, like common side effects of HIV medications. So, and we need to figure out a way to incorporate this domain knowledge to our method. So by the way, here's software we have already built. So if you're interested, I can send you the link. So essentially you click the start now and then you input the information, we will give you the recommendation. Yeah, but anyway, so here we try to see, okay, how can we incorporate? And I tried ChatGPT 4. So I asked the question, okay, suppose you are an AI physician and you have an HIV patient whose very load is 10,000, BMI is 22 and has diabetes. What's the top 5 ART regimens would you recommend? We know that, ChatGPT usually, suffers from hallucination. And we found out some answers actually is okay, but some they are faking the result, but some are okay. So it's kind of like not good enough because I don't want to criticize because they also have a lot of fake information. But just ChatGPT is not enough. So people would think, maybe we can do the fine tuning, right? So now people doing a lot of things like fine tuning and they use the reinforcement learning to fine tune their large language model. So my group now currently is doing that is like we kind of manually write down a lot of rules from the clinical guidelines. So and also like drug-drug interactions. For example, if this person is using certain drug, then it's better to avoid some ART drug. And also we download the data from Stanford databases about the mutation. Like if you have specific mutation, then also this drug has, strong interactions, better to avoid. So we have a lot of this expert information we have already, summarized. And we're trying to see if we can combine the large language model with reinforcement learning so that we can, utilize this information into our recommendation. Okay, so basically it's, it's large language model plus reinforcement learning. And next step is we want to add the human feedback. So essentially the framework is like this. So we are currently working on this. So the key idea is that now we have this reinforcement learning model and we have this domain knowledge. So we can have recommendations and we have clinician collaborators, right? So they can review our recommendations and see if this is good. So it's basically here is like expert knowledge to ranking our recommendations. So we are still thinking about what's the best way for them to rank because I don't think they will say it's 1 to 100, right? It's impossible. So we're still thinking about a good strategy to reduce the clinician's workload, but help us to refine our results. And after they have the ranking, and then we can retrain our model based on this, like human feedback and reinforcement learning. We can retrain our reward model and then further improve our reinforcement learning algorithm. So that's kind of like the part we're working on right now. Okay, there are future work. So that's we can incorporate more factors in reward function, and we are also doing the polypharmacy for aging population because we actually have a lot of non-ART drugs information. So how can we, infer the underlying conditions based on this polypharmacy data? And also there are a lot of unmerited confounders. So for example, my group has been developing, theory for the reinforcement learning methods in poll MDPs, partially observable MDPs. So we want to incorporate this to the framework. And also a lot of theory methods, like for example, how to better quantify the state action pair uncertainty, because uncertainty is very important for the clinical decision making. And also like theoretical guarantee, and also some stochastic decision and versus deterministic decisions, like how flexibility we want to give to clinicians. And also like lastly, I want to mention like Peng said, here this economic state, but for Peng's question, for reinforcement learning state, we indeed need to predefine the weights for the enrolled function. But we found out actually, each individual, they may have different emphasis on different components. So we are currently, the Dapeng leads the HIV AI care project, and his next project is actually, we're trying to see if we can develop a method that actually optimize the individualized reward. Because, reinforcement learning method, they basically, you need to define reward function to optimize the policy. But think about it, if everyone has a different reward, then how can we optimize the policy? So now that's a part we're working on right now. Okay, so that's all. Thank you.